So then second thing we require, so I am not going to talk about the digital filter, I mean that's usually the DSP. So if you take the DSP, because it requires almost like a 10-15 class complete to design a digital filter, okay. So usually I mean this is out of the scope of the analog design, basically the filtering portion. So what I mean obviously it's everything is done Verilog, so I am not going to teach you Verilog here. So all you need is just a filter code and synthesize it, that's it, it will give you the filter. So you are not going to design gate by gate logic and everything, that will take forever. So you all have to do just write a Verilog code for your filter and synthesize, it will give you the filter right away. So then the second thing you require DPWM, which is digital PWM. So after your compensator, or if it's a PID, then it's a digital PID, then output control voltage is going to fed to DPWM and you have to convert it to PWM. So the resolution of DPWM should be higher than resolution of ADC to avoid limit. If you remember the limit cycle, we talked about limit cycle in digital LDOs. Okay. So the resolution of ADC, the resolution of the DAC, the current DAC or resistive DAC, whatever you are using to regulate your output, should be more than your ADC. And DPWM is nothing but a DAC actually. It is converting your digital code into PWM, which is time. Okay. So if your DPWM resolution is less than your ADC, then you will get limit cycle, the same problem. Your output will never settle and keep bouncing between plus minus 1 LSB and you will get this kind of behavior. But if your resolution is, let us say, 1 bit higher, so ADC is, let us say 10 bit. When I say 10 bit, again do not think about that literally 10 bit, but the delta step we are talking about, which means the delta or LSB size of your ADC, which is, let us say 1 millivolt, then 1 LSB change in DPWM should be less than 1 millivolt change in the output, which means your resolution is higher than that. Whether it could be 3 bit, 4 bit or 5 bit, it does not matter in that case. Okay. So then it will settle. But the problem here is, I mean for ADC we know we do not require a full range, but here your duty cycle depending upon output voltage. So during transient I know my the variation in the duty cycle may not be that large, okay, until unless you are basically doing a non-linear kind of behavior and stretch your duty cycle all the way to 1. But if you are, let us say you have to cater to in steady state wide range of V out over V in ratio and your duty cycle may vary from 10% to 90%. So you are still looking at 80% range here, then the number of bits which you will require in the DPWM would be much higher compared to your ADCs, even if your step size remains same. Okay. So the brute force way of doing that DPWM, so let us say I am operating at 1 megahertz clock, I am looking at a 10 bit resolution which can give me a 0 to 100% duty cycle. So 10 bit is 1024, so you can count with the high frequency clock. So let us say I have a 1 gigahertz clock. So 1 gigahertz clock will count 1000 in for 1 megahertz one cycle and 10% it will count how many? 100, okay, 1% 10. So that is how you do actually. So you can get a 10 bit resolution by just feeding a high frequency clock and counting it, and depending upon your code, I mean you are resetting it every positive edge of 1 megahertz. So setting the duty cycle at positive edge of 1 megahertz and you reset it based on the counter. So basically your control code which you are generating from PID, that will control the count. So how many counts you require, based on that it will reset the duty cycle and you can vary the duty cycle. So this is what is happening here actually. So when the error, this is your error code, and error code, when I say it is basically the control code here. So when your counts goes above, you reset your duty cycle, just like in case of ramp, when your control ramp was going crossing your control voltage is what resetting. So the ramp is now more like a digital here, you can say, because it is nothing but your counter. Okay, so then you will get this. So but the problem is 1 gigahertz clock is not simple to design the oscillator. It is going to take lot of power. 180 nanometer, I mean if you say like it may consume a lot of power. So that's a one problem. So what we do, we use DLL based. So in the DLL based, you can still feed the same 1 megahertz clock and have, let's say 10 bit resolution, you can have 1000 taps. So you can think about, you have a 1 megahertz clock, 1 microsecond delay, which is 1000 nano, okay, and you have 1000 delay cells, each giving 1 nanosecond delay. So you have 1000 phases spaced by 1 nanosecond, and depending on the code at which phase you want to reset the DPWM, you will get a similar behavior here, exactly same behavior. So the code will decide which one to phase to pass to reset, and set is always appearing at the positive edge of your 1 megahertz clock or so. So this is how it will be looking like. Each phase will be delayed based on your resolution. So but then again you require 1000 delay cells here, and you cannot match each delay cell. So 1 nanosecond, one might be like half a nanosecond or something. So matching is a problem. So you may get a random delays actually here instead of equally spaced these delay cells. So what we do actually, so we limit the resolution. One way could be you limit the resolution. So instead of 1000, I will use only 100, let's say. The same thing you can do here also. So instead of 1 gigahertz, let's say use 100 megahertz. So your now resolution is 1% only, okay, but 1% is a basically large step. It may cause a transient in the output when you change the duty cycle. So you go from 50 to 51%, you will see the transient in the output, large transient, which may be unacceptable. So then what you do actually, you dither, and dither we already talked about. If you remember the pulse skip mode and even in the buck boost mode, we are talking this number of buck and this number of boost, or this number of 100% duty cycle and 90% duty cycle, the D max you were dithering between. Same thing you can do here also. Okay, if you remember even the this subharmonic oscillation in current mode, what happens? It basically alternately changes the duty cycle, but on an average. So let's say 25, 75, and on average 50. So let's say I have a 1% resolution here. So between 10% and 11%, I can dither. So one cycle of 10%, another cycle of 11%, it will give me 10.5 on an average. If you want more resolution, then one cycle of this, two cycle of the other. So basically 1:n or n:1 kind of code you choose, and you can keep dithering. So dithering could be like two types. One is the fixed ripple frequency dither, other is variable ripple frequency. So when I say fixed ripple, so let's say I have a one cycle of 10% and one cycle of 11%. So I am getting 10.5%. But now 1% of 10 and one cycle of 1% and two cycle of 11%. So what you are getting here? Slightly more than 10.5. Okay. So now 11% is two cycle and the 10% is only one cycle. But your dithering frequency is changed now. So you'll have a two tones here. One tone will be coming at PWM frequency, other tone will be coming at dithering frequency. When I say dithering frequency, so this is one duty cycle and these three cycles are, let's say, different duty cycles. So on an average, you will get each cycle may have a same frequency, but if you look at, you have another tone, this is your dithering frequency, which means one cycle of this and three cycle of this. So it will be looking 1/4 of your PWM, correct? So because total is 4 cycles of this, but the same thing I can achieve by doing 1:1 I want. So what if I do, let's say 2:2? If I do 2:2 and 1:3, the number of cycles will remain same total in the dithering frequency. So your dithering frequency remains fixed, but depending upon what is the level of dither, that is the frequency you will require. You may require 10:1 10 actually, or 20 is to 20. So the dithering frequency will be much lower, so your output ripple will be large at that particular frequency, the lower frequency which is coming due to dithering. So that's why you always prefer this variable frequency, where if I require, let's say, same number of cycles, so instead of choosing, let's say, 10 is to 10, I will always choose 1 is to 1. So I will keep one fixed to one, other increasing, and in the other case, so you can choose 1 is to n or n is to 1. So that is the better way, so that one is always one cycle, other is changing. Instead of using same number of cycles in the both, then you will have a low frequency tone here and your ripple will be large. So another option could be delta sigma based. This is nothing but more like a dither actually. So how you dither it? So what you do, let's say I have a m bit code. So m minus, so n bit is going to the delta sigma. So let's say I have a 10 bit. So 3 bit I can feed to my DPWM and 7 bit I can feed to delta sigma. So what delta sigma do? It will automatically generate a code which will dither between these, and so 3 bits mean you have 8 levels. Okay. So from 8 levels you have to generate, let's say, 1000 different values. So what that delta sigma will do from that 7 bit, it will choose which one to use and how many cycles of that. So it's doing nothing but selecting between like which the n and which will be 1 and which will be n, that's it. And those n could be values out of this 7 bit. 7 bit is 128, 127, basically 0 to 127 you will get. So from each level, so now you can think about, this is doing a coarse DPWM, the fine control is coming from the delta sigma. So I have sliced, let's say, in 8 levels my DPWM. I mean 8 levels is actually very low, but you can think about again the same case where we were talking about 100 megahertz clock or 7 bit. So 7 bit is also usually on the higher side. So let's say I have a 4 bit. 4 bit is 16 code total. So let's say I have a 16 levels. I have sliced into 16 levels, and those 16 levels, between the two adjacent levels, I can create one 7 bit combination out of that. Correct. So each, and that will be for each level. So you will be getting a 127 multiplied by 16. So that high resolution you can get. Okay. And if you want a total 10 bit, then 4 bit versus 16 bit you can, 6 bit you can do. So you can do a 6 bit in the delta sigma. So it's up to you, like you can split into 5:5, 5 bit here and 5 bit there, and or 3 bit here and 7 bit here. So it all depends on you. I mean, what is the resolution, maximum resolution you can achieve from DPWM. After that, everything can be taken care by delta sigma. Adaptive compensation. Okay, so we talked about the advantages of your digital control, because it can adapt to any changes in the L and C or any other parameters which may change dynamically or due to process or even voltage or temperature. So, and another advantage of this adaptive compensation is plug and play actually. Plug and play means you have you have given a converter to a customer without bothering about what L and C he is going to put. So he can choose any L and C, and your control loop will adapt to that L and C and place your zeros and poles and gain, everything will be set inside. So which means you need to know the value of L and C for that. I mean, in order to compensate, what all we needed? We mostly needed the L and C. Once you know your resonance, after that you need to look what gain you have to set based on your loop gain, the uncompensated loop gain, whatever, and based on that you decide what gain you need to choose, Ki or Kp, to get UGB at your required or desired value. So the tuning method, there are multiple, like this is a paper, there are different tuning methods. When I say tuning methods, it's basically the adaptive compensation, nothing but. So you tune your parameters based on your changes in L and C or any other parameters. So, this Middlebrook method, so this is nothing but to look at the gain, loop gain without breaking the loop, correct. So, one way to look at the your phase response, and so when we open the loop, we look at a UGB and what is the phase margin at that, okay. But if you look at the closed loop, what will happen? So, that will be unity gain, correct, and then whatever phase you get there it will basically tell you that is the phase margin, correct. So, what it does, it injects the signal and wait for this output to get a, so you tune the frequency, and at what frequency it becomes a unity gain, you look at the phase delay in the two and you can get both phase margin and your UGB, correct. So, that is what you do in the closed loop, and you can basically, and once you have your phase margin, you know the UGB, UGB you already know, and you know phase margin, that is what you are interested in. I mean, ultimately when I want to measure the L and C, the reason I want to measure L and C, I want to fix my phase margin and UGB. But if you can directly measure the phase margin and UGB, then I do not need to know L and C. So, that is what it does actually. But the problem here is you need to inject a signal. So, on the fly you cannot do, your output may get disturbed. So, the signal which is injected here, it will appear in the output. So, it may cause a disturbance in the output. So, this is not a very clean method. Another method is again, it is the same thing, but done in like a whole kind of so yeah, these two are actually same. This is just showing you how you implement the, how you inject the signal, and then you need to have a band pass filter. It is a very complicated because you need to inject a sinusoidal wave at one particular frequency only. If it has multiple frequency, then it is very hard to know where UGB is, because UGB will appear only at one frequency. So, you need to have a very narrow band signal. So, that is why you need to use band pass filter here. So, another method is correlation based. So, and this is very complicated, it requires a whole DSP to implement this. So, they are literally measuring the, actually looking at the FFT here, which means frequency response you are looking at. So, it has its own like all digital here, and this, I mean the paper they have shown, this was whole implemented on FPGA. So, why would I use a whole FPGA to build a DC-DC converter? It does not make any sense. So, this is another method which is basically limit cycling oscillation based. So, what they do actually, they, if you look at this response uncompensated, what will happen? Yeah, this is uncompensated, and they literally force it in unstable, but the instability, I mean they want to make sure that when it is unstable, the amplitude is not that large actually, okay. So, they force is into limit cycle, which means you keep on, let us say, increasing the your UGB or whatever your gain, let us say I am tuning the gain. So, whenever it crosses this omega naught, it will start oscillating at omega naught frequency. So, if you have enough gain here at omega naught, then it will always oscillate at omega naught, and that frequency will tell you where the omega naught is or the resonance frequency. So, once I know resonance frequency, I can tune, but again the problem is I cannot do it dynamically, because it will again cause a disturbance in the output. So, these are the limitations with the existing techniques. So, simplified tuning techniques could be like I can give a step signal or impulse at the input, and so in the open loop, let us say I give a step at L and C, what should I expect? The ringing, okay, and the ringing frequency will tell me omega naught. So, this is the simplest way we can implement. So, can I measure the Q also here? If let us say I want to measure the Q, how do I measure? So far what we have seen, we can say that ADC is not a big constraint for DC-DC converter, especially if you are looking for a smaller range. So you don't need a like a 10 bit ADC with a very high resolution. I mean, you can achieve that same resolution with by limiting the range of the ADC, because you are only basically catering to the change in the output during transient plus minus 50 to 100 millivolt. Okay. So then so one thing you have to remember, for this you have to consider that reference is fixed. If you are changing the reference, then common mode is changing. So then you may require a very large wide range ADC. So if your feedback voltage remains fixed for all the output voltages, if you are changing your output voltage only with the feedback resistor, then you can limit the range of your ADC. But if you are changing the output voltage with the reference, then ADC input voltage is changing, then you may require very wide range. So designing high resolution DPWM is a challenging task for faster loop bandwidth, as dithering slows down the loop. So we talked about this. If you want to increase the resolution, you dither between two duty cycle. So which means you are slowing down the loop. I mean, if let's say my dither level is much higher, you are doing a 1:n is like, say, 1:10. So you have to wait for that many cycles to settle your output. You cannot change the code before that. So you are basically slowing down the output, or the loop actually. So because output will take long time to settle. So as you keep increasing the order of your dithering, basically you are limiting. You have to limit your bandwidth. You don't have any option. And if you using a very high order dithering with a faster loop, then it may become unstable. So, and also we saw that there are different techniques for adaptive compensation, but most of them look very complicated, or they cannot be used in normal operation because you will get disturbance in the output. So the existing adaptive compensation techniques can't be used in dynamic supply applications such as RF power amplifier and class H audio, where supply is modulated with RF envelope or audio signal, because test signal fall into a signal frequency range. So you have a test signal. I mean, most of them, there were couple of them are using test signal. So which means your, I mean, obviously it should be more than the output ripple. If it's less than the output ripple, then you cannot detect it. So which means you are introducing more noise in the output, and if it falls within your signal range, then it will corrupt everything. So you cannot use. So then we looked into simplified technique, where we are only like using a step or impulse response, you can say, and this can be achieved by using when you are starting your converter. During that time you can do that before the output gets settled, and you just look at the ringing frequency of the output, that will give you the omega naught. And if I want to, I mean, usually Q may not be required, but let us say in case you want Q also, you without measuring the amplitude of the output ringing, you can simply look at the number of cycles it rings for, and you can very well relate that to Q. It may not be that accurate, but even if you are, let us say, within 20-25%, that is fine. So then we know that HLC is this, so omega naught can be related to this, Q naught can be related to this, and then under no load condition, that is what we look for, worst case Q naught. So most of the compensation we do for no load. So this will become a square root LC over C cross, and omega naught is 1 over square root LC under no load condition. So, and R loss can also be calculated. We know that V loss is nothing but D times V in minus V out. Okay. So, if we can measure the average of your switching node and take the difference between V out, that will be the loss in your basically inductor. And if you look before the gate driver, the PWM, then that will include the power FET loss also. So, you can separate out even inductor and power FET losses. So, that is not difficult to do, and R load, obviously I load, if you know, you can measure R load also. So, all the measurements can be done very easily, and in fact, if you can, let us say I have a current sensor and I can sample this RAM, then you can calculate your L also. I mean, we have omega naught information, but if I want to calculate, say, L and C naught separately, then you can do that also. So, L I can calculate by simply measuring the slope of this and that you can do sample one here and another, take a sample here, take the delta, and from there time you know, and you can very well get the inductor value from here, L equal to V in minus V out over M2, where M2 is the slope of this falling or rising slope, which whatever you want to use, you can use either of them. So, most of the time if you are operating at, let us say, I mean we talked about when you are using a current sense, then depending upon what duty cycle you are operating, your bandwidth requirement is very high. So, if you are operating at very low duty cycle, then rising slope may be faster compared to falling slope. So, if you are only measuring the inductor, then you should always look for which has a higher time, which means here you are operating low duty cycle. So, you get more time during T off. So, you can measure this slope, because both of them will give you the same information, and we are interested in only L. And once you have that, you can calculate your C, output capacitor. So, one thing you have to remember, this requires some maths, and that is why it's everything is done digital. So, you require ADC. Once you get from the ADC you get the output, you can do divide, multiplication, everything, and get all the values in digital. Okay, so that's how you do basically. Once you have those values, you know how to tune your parameters, compensation, I mean omega Z1 and omega Z2 and gain, and you can very well do that. So, you need some algorithm to run at the background, which will keep doing this, and you can do this at a background in the normal, I mean operation also. So, during a startup you can measure this omega naught. So, place your omega Z1, omega Z2, you have started and you have made sure that now my converter is stable, but you cannot ensure that you have optimum bandwidth, let us say 1/10, and I want to achieve always 1/10 bandwidth or the best bandwidth and phase margin across all the condition. So, any dynamic changes, let us say once your converter is running, I mean due to your change in input and output voltages, or due to change in any other parameters due to temperature, your location of your omega naught may change. It is quite possible, or your gain may change if your V in is changing or V out is changing. So, then you have to adjust your parameter accordingly. So, those things can be done on the fly in the background. This will be running because you are already measuring your L. Okay. So, if there is any change in the L, that can be taken care of. Okay. So, as we know that designing I mean DPWM or digital PWM is not easy, especially if you are running at very high frequency. Let us say I am running at 10 megahertz. So, it is not very simple actually if I want 10 bit kind of accuracy. So, alternate way could be like you just use an analog RAM and you convert your digital code into analog voltage by using high resolution DAC, and doing a high resolution voltage DAC is easier compared to doing a DPWM.